Okay, in this video, I'd like to walk through the practice test that I assigned through Schoology. Coming up soon, you're going to be taking your test for 5 for trigonometry, and then shortly after that, you'll be completing the final exam. So this section of the class historically has always been the most difficult portion of the class, and unfortunately, we've been trying to complete this on home instruction. So my goal is to create a test to cover this content that makes it fair and equitable for all parties here. Rather than giving you the test 4 or 5 on paper next week, I will make a Math Excel test and release that and make that accessible to you. For the final exam, however, I will require a paper copy of the exam for which you can download and print out, or you can just complete on a sheet of notebook paper. Either way, you'll do your work on paper, take pictures of it, and send it back to me for grading. But more on that later. As far as this test goes, I just put together the answer document and I've posted that PDF to Schoology. I'm just going to walk through my work here and offer commentary over a handful of these questions, or maybe all of the questions, depending on how timing goes. And hopefully that clarifies some of the questions you may have about my approach. If you have further questions, then by all means send me a message and we can chat about it. So on problem number 1, well, first off, the instructions said to complete the following equations. Your answer should be numerical. So on the blank copy, we were given this, and our answer key says the answer should be -1. Well, how do we get there? Well, I ended up using a Pythagorean identity and replaced secant squared with tangent squared plus 1. And then when we combine like terms, the tangents cancel and we're left with -1. And that's how we obtain -1 as a solution. For number 2, I'm using an even-odd identity. I recognize that cosine of negative theta is just the same as cosine of theta. And since cosine theta minus cosine theta cancels to 0, then we have a solution equal to 0. Now keep in mind that on a test like this, when we're talking about trig identities and trig equations, just writing down the final answer is really no good. You've heard this throughout your entire mathematical career, I'm sure, that work is important. Well, in this type of test, you showing your work is essential because it's not about getting the final answer. Certainly, we could use calculators or websites to give us the final answer, but you really have to show your process along the way. I want to know that you understand the process or the navigation to get to the final solution. So that's really what I'll be looking for. Final answers are good, right? Correct and final answers are good, but work along the way, of course, is better, and in this case, absolutely required. For problem number 3 here, I went ahead and FOILed the 2 binomials that we have. So there's a binomial here, and I FOILed them together. First term ended up being cosine squared. The outside term was a sine times cosine. The inside term was also sine times cosine. So I got 2 of those, 2 sine, cosine, and then the last term, sine times sine, gave me sine squared. Well, I also recognized that cosine squared plus sine squared is equal to 1, according to our Pythagorean identity, and 1 minus 1 ultimately cancels to nothing, which leaves us with the fraction 2 sine theta cosine theta over sine theta cosine theta. The sines and the cosines cancel, and we're left with 2, and that's how we obtained that final answer. For questions 4, 5, and beyond, I think we've got, oh no, 6 and 7 are a little bit different. So for questions 4 and 5, our instructions are to establish the identity, and your answer should be written in the form of one trigonometric function. So when we're done, we should have a single trig component. So sine, cosine, tangent, secant, cosecant, or cotangent, but not a fraction or a combination of any others. Okay, sorry about that. Got interrupted by a phone call. So I think I was right here starting to talk about establishing the identity. So generally what we do is we work on the left side of the equation. We work with the material that's on the left side here and try to make it look like what the right side of the equation is equivalent to. So in this case, I'm rewriting tangent theta using the reciprocal identities. Tangent theta is now written as sine over cosine, and cotangent is written as cosine over sine. I'm going to ignore this sign out here for just a second. I'm going to try to clean up what's on the inside of the grouping symbol first. My goal next would be to add these two fractions together, but in order to do so, I need to find a common denominator. So on the left-hand fraction, I've multiplied by sine over sine. That's a form of 1 that's going to change the way this fraction looks, but it doesn't change its value. So that's going to leave us with sine squared in the top of this fraction on the left. Similarly, here I'm going to multiply by cosine over cosine, which leaves us with cosine squared on the top of that fraction. Both denominators are now the same, sine times cosine or cosine times sine, depending on how you want to look at it. Either way is fine. Sine squared plus cosine squared is equal to 1 according to our Pythagorean identity. So I've changed this numerator, this entire numerator, to the number 1. And now I've got the fraction 1 over sine times cosine. At this point, I'll multiply the sine value back in to the fraction, which would allow the sine theta over sine theta to cancel or reduce to 1, and ultimately we're left with 1 over cosine theta. Now that's okay as a final answer, but to be perfectly honest, I prefer secant theta more because it's a single trigonometric value as opposed to a fraction including a trigonometric value. But I would accept either on paper. Math Excel, depending on their instructions, may not accept this one in green. For number 5, we've got a similar approach. I've got a product of two binomials that I would argue need to be FOILed together. In doing so, the outside product gives us cosecant squared, the first products give us cosecant squared. The outside and the inside products are cosecant and negative cosecant that cancel each other out. And with those middle terms gone, then we're left with cosecant squared minus 1. And cosecant, according to our Pythagorean identities, is the same as cotangent squared plus 1. So cosecant can be replaced with cotangent squared plus 1. And cotangent squared plus 1 minus 1, of course, those two will cancel, and we're left with cotangent squared. Now, it would be nice to have just a single trigonometric expression, but that's just not possible in this particular case. It is cotangent squared, and there is a single trig expression. It just happens to be squared. Moving on to number 6, we're told to use a sum or difference identity to find the exact value of the trig function. We're going to simplify our answers using any radicals. So the goal here is to avoid any calculators. Now my instructions won't say calc versus non-calculator because this is a take-home test and exam, so it'd be very hard for me to differentiate. But what I would like to see is the work that you would do by not relying on a calculator. So of course you can check your work along the way with a calculator, but again, show me the process. How do you get to this final answer if that's the answer that the calculator gives? Moreover, if your calculator is not one to provide an exact answer, well, then we have to do this by hand and produce a result. Sometimes the decimals just aren't accurate enough or aren't appropriate enough for a particular problem. So anyway, what I see is cosine of 15 degrees, and my brain thinks of 15 degrees as 45 minus 30. So I would use a difference identity for cosine, and the difference identity requires cosine times cosine, sine times sine, using the two angle measures that I choose with an addition sign in between. So evaluating each of those components, I've done these mentally. I'm thinking of the unit circle here. Cosine of 45 degrees would be the x value at 45. Cosine of 30 would be the x value at 30. And similarly, sine 45 is the y value at 45 degrees, and sine 30 is the y value at 30 degrees. So mentally, I've considered those, performed the multiplication to get square root 6 over 4 plus square root 2 over 4. Since they have a common denominator, I would add them together. I like this answer personally on the left-hand side, but in seeing this question on Math Excel, I know they're going to lead you to this answer on the right. I would accept either, and I do believe that Math Excel will accept either as well. For number 7, this one gets pretty interesting because it's the sum identity for tangent, and there are several fractions that develop with tangents. Not only the identity contains a fraction, but the solution to each tangent function requires a fraction as well. So I see 165 degrees as the sum of 135 and 30. And so using the appropriate sum identity, I need tangent 135 plus tangent 30 over 1 minus, it's important to change that sign to a minus during the sum identity, tangent 135 times tangent 30. Now here again, I'm evaluating each of these trig functions by considering the unit circle. 135 degrees is this position here, and so the y-coordinate divided by the x-coordinate, so y-coordinate is radical 2 over 2, divided by the x-coordinate, which is also radical 2 over 2, divides to equal negative 1, except that x-coordinate was negative radical 2 over 2. That's where the negative 1 comes from. For tangent of 30, we're thinking y-coordinate of 1/2 divided by the x-coordinate of radical 3 over 2. Those denominators of 2 eliminate themselves, and we're left with 1 over radical 3. So I've executed those just fine. The only thing we can really do to simplify this expression before rationalizing denominators and cleaning that mess up is to distribute this minus sign with this minus sign. Two negatives that multiply together make a positive. Now, me personally, I'm okay with this as a final answer then. I don't mind having radicals in the denominator of any fraction. So I would stop there personally. However, if you're using Math Excel's guidance, then they would require that you rationalize the denominator and eliminate all fractions if possible. So that's quite a lengthy process from this solution that I just established. We need to find a common denominator. So this negative 1 and positive 1, we're just making a common denominator. I forgot my radical sign there. So that leaves us with negative 3 plus 1 over negative square root of 3 plus 1 over square root of 3, and positive square root of 3 plus 1 over square root of 3. In this complex fraction, the two denominators, radical 3 and radical 3, can cancel. But that now leaves us with a single fraction, negative radical 3 plus 1 over radical 3 plus 1. And to eliminate the square root in this denominator, we have to rationalize the denominator. And that's done by multiplying by its conjugate. So instead of multiplying by radical 3 plus 1 again, we multiply by radical 3 minus 1, and we do that on the numerator as well as the denominator. By foiling those two together in the denominator, we see the two radical signs cancel. In the numerator, the two radical 3's are going to combine. Negative 3 minus 1 is negative 4, plus 2 radical 3. And then in the denominator, 3 minus 1 is just 2. There's a common factor of 2 in the numerator, so I've factored that out to the front. That 2 that's common in the numerator factors with the 2 in the denominator, ultimately leaving us with negative 2 plus square root 3. Now, if you've got a calculator in front of you, you can verify that this answer over here was correct, because when you punch it into the calculator, its decimal value should be the same as whatever you get at the end over here. So while it's additional work, personally I don't find it necessary when we're talking about exact solutions. But the way Math Excel is set up, they may require you to do that. And now you've seen that process in its entirety. For questions 8 and 9, our job is to find the exact value of the expression using an appropriate sum or difference identity. So we're starting with this in black here, and we're trying to find out what that's equal to. Well, you just have to be able to identify which sum or difference identity is being used. when we have sine times cosine plus cosine times sine, that's the pattern for the sum identity for sine. And since this is the sum identity for sine, then we just use sine evaluated at the sum of these two angle measures, which happens to be 30 degrees. Of course, the y-coordinate at 30 degrees is equal to 1/2, and that's how that solution was obtained. For number 9, we've got cosine cosine minus sine sine. When we're multiplying by the same trig value, that's an indicator for an identity for cosine. And with the subtraction symbol in between, that's actually an indicator of the sum identity for cosine. Go back to day 53, 54 to see those identities written in place. The x value at 30 degrees is radical 3 over 2, so that's how this solution was obtained. For numbers 10, 11, and 12, remember that on these problems over the last couple weeks, we could think of them as positions inside the unit circle. However, it ended up being a little bit easier to solve when considering triangles oriented at the origin. So if sine of theta is equal to 15 over 17, then the angle measure shown with this green ray here, the angle measure here must be sitting in the first quadrant according to our description or our restriction on the angle measures. And so therefore the opposite side length is positive 15 and the hypotenuse side length is 17 based on the sine values. And if the opposite side length is 15, the hypotenuse is 17, we can use the Pythagorean equation to find our adjacent side length. And now we know that all three side lengths, we can now establish what sine, cosine, and tangent is for each, or for the angle measure. That's helpful because the double angle identity for sine anyway, requires 2 times sine times cosine. We knew that sine was 15 over 7, but we now know that cosine, which is the adjacent side length divided by hypotenuse, is 8 over 15. So the product of these three fractions is 240 over 89. And we got that precise solution, perhaps without using a calculator, but we've got that without knowing what the angle measure itself is, which is really important. For number 11, recall that there are 3 different double angle identities for cosine. I just happen to use this one. Cosine of a double angle is equal to 1 minus 2 sine squared of the individual angle. We already knew what sine was, 15 over 17. We square that, multiply it by 2, subtract. So after we subtract 289 minus 450, we get negative 161. The two denominators had to be common before we subtracted. That's why we created this fraction on the left. And we've got a denominator of 289. For tangent of the double angle, we need this expression, 2 tangent theta over 1 minus tangent squared theta. So again, tangent being the opposite side length over the adjacent. I'm using the fraction 15/8 in that position. I went ahead and simplified this without a calculator, and I would suggest that you do the same. But 30/8 divided by finding a common denominator minus 225 over 64 left us with negative 161 over 64. When you're dividing two fractions, that would be the same as multiplying by the reciprocal of this fraction. And so 30 times 64 over 8 times 161, negative 161. These two had a common factor of 8 that canceled, but nothing else did. So 30 times 8 was 240. 1 times negative 161 was negative 161. And we got that final answer here. For part 2 of the test 4-5, this is where we're actually going to be solving some trigonometric equations. And the goal, of course, is to isolate theta, try to solve for theta. In this case, subtracting 4 and dividing by 2 leaves us with negative 1/2 on the right-hand side. And we have to ask ourselves, where in the unit circle? And so the two positions inside a unit circle that have y-coordinates that are equal to negative 1/2 are at 7 pi over 6 and 11 pi over 6 radians. Now, I've noted, or hopefully you noticed, I should say, that we've switched to radian measurements here because our domain restrictions are indicated in radians. For questions back here, let's see here. The instructions didn't say anything back here, but the problems themselves were given to us in degrees. I thought there was another. Yeah, well, our domain restrictions are what we're looking for to identify whether we're operating in degrees or radians. I think we might see some more examples of that here shortly. With number 14, same sort of thing. We'll divide by 4 and then take a square root on both sides. When we take the square root, though, we've got to be prepared for both positive and negative solutions. So where does cosine, where does the x value equal a positive root 3 over 2 or negative root 3 over 2? Positive root 3 over 2's exist here at pi over 6 and 11 pi over 6, and negative root 3 over 2 for our x values are over here on the left-hand side. And for number 15, number 15, now this is one of those that's going to require some additional rotations to find all solutions. We know that sine of 3 theta is equal to 1. Well, the position in the unit circle that's got a y-coordinate of 1 is right here at the top of the circle. But that only happens one time around the unit circle. So we'd be tempted to answer with just pi over 2. But you should recall that it's not theta that equals, not sine of theta that equals 1, but sine of 3 theta. So 3 theta has to equal pi over 2. And after we divide pi over 2 by 3, we're left with pi over 6. But pi over 6 isn't the only answer between 0 and 2 pi that answers this question. If we were to take an additional trip around the unit circle twice and 3 times over, these numbers don't exist inside the unit circle anymore. Those angles don't exist inside the unit circle anymore. But after I divide each of those by 3, we do end up with angle measures inside of a unit circle, or within 0 to 2 pi. And so that's the reason we had to go around the unit circle 3 times to identify these potential solutions, so that when we divide at the end, our answers do exist inside that domain. For number 16, subtract 2, divide by 3 radical 2. The 3's will cancel, and we're left with negative 1 over radical 2. And negative 1 over radical 2, hopefully by now you recognize, is the same as negative radical 2 over 2. And the position in the unit circle where x is equal to negative radical 2 over 2 are at 3 pi over 4 radians and 5 pi over 4 radians. Here's an example of a trig problem where we're going to answer in degrees. So again, the instructions weren't explicit about saying to put your answer in degrees, but the angle measure restriction, the domain restriction, was in degrees, so that's what we're going to go with. Now, sine of theta is supposed to equal 0.18, and the way we would solve that using a calculator, and of course we would use a calculator for this one, is we would enter sine inverse of 0.18. But the calculator is only going to give us one solution, and that's 10.3698 degrees. I am interested in both solutions, though, so let's keep in mind that if sine of some ratio is equal to 10 degrees, well, that's this position here, 10 degrees off of the origin. There's another spot inside the unit circle that has the same y-coordinate on that, on that unit circle, and that's way over here. And the way we would obtain that in this case is to take 180 degrees minus the 10.3, and that's what gave us the 169.6 degrees. For number 18, similarly, we would take tangent inverse of 7. The calculator is going to give us this answer, 81.86 degrees. However, that only represents this solution. The other position inside the unit circle that has the same y divided by x result is down here in the bottom left, which happens to be an additional 180 degrees beyond. So we're going to take the answer that the calculator gave us, add to it 180 degrees, and that's where the 261.56 comes into play. Although I think there's a typo there. Yeah, this one should be 86 as well. So 8699, 8699. There we go. For number 19, again, using the calculator, cosine inverse of negative 0.91 is going to return a result of 155.5 degrees, which represents this angle measure. The other position inside of a unit circle that has the same x value is down here below it, and we could try to figure out what the difference between these two angles are and add them to 180, but I find that it's easier in the case of cosine to just subtract this value from 360. So that's what's going to give us this position over here, and it'll be written in terms of a value between 0 and 360 degrees. And that's where the 204 comes into play. For number 20 and problems like it, first you need to make sure that the trig function's by itself. So we added 5 and divided by 6 on both sides of the equation. Then evaluate cosine inverse at this fraction. That's going to give us a nice angle measure. Since this is cosine, I'm going to subtract this angle measure from 360, and we'll find the other position that has the same x value to be at 326 degrees. And for the final two questions of the test before the bonus, we need to solve the equation that's provided here, and they look like quadratics to me. So if it helps, you can change. I like changing sine to the letter y, and I like changing cosines to the letter x. And in doing so, it looks more like a quadratic equation that we may be comfortable with from our Algebra 2 days. So if I'm looking at this and say that 7y squared minus 16y plus 9 is equal to 0, certainly we can use the quadratic formula to try to solve for y, or you can try factoring. I chose to factor, knowing that 7y minus 9 times y minus 1 would FOIL back together to make 7y squared minus 16y plus 9. Now we're not solving for y in these problems though, but we're solving for theta. So I made that back substitution and changed y back to sine theta. And since each factor should be set equal to 0 when the product is equal to 0, we now know that sine theta equals 9/7, or sine theta is equal to 1. Now the position in the y, or in the unit circle where the y coordinate is equal to 1 occurs at 90 degrees, and the position in the unit circle where y is equal to 9/7 doesn't exist. 9/7 is a fraction bigger than 1, and there's no position inside the unit circle that's got a y coordinate bigger than 1. So it's impossible to find a solution from this. The only solution exists over here, only real solution I should say, exists from this factor, which is at 90 degrees. For number 22, we're going to use a combination of both substitutions and trig identities. Since we have cosine over here on the left, I distributed the 12 in, and then I thought about changing sine squared into some form of cosine squared. And I did that with a Pythagorean identity. Pythagorean identity helps us to realize that sine squared plus cosine squared is equal to 1, so therefore sine squared by itself is equal to 1 minus cosine squared. And that's where this substitution came into play. I moved these two components to the left side of the equation by subtracting and adding appropriately. And we have this expression here, cosine squared minus 12 cosine, whoops, should not be squared, 12 cosine theta plus 11. Factored that by imagining this as a letter x squared and 12x in the center. I didn't bother writing it down because I was able to factor that mentally. And cosine theta minus 11 must equal 0, and cosine theta plus 1 or minus 1 should equal 0. So we add 1 to both sides here. The only time that the x coordinate is equal to 1 is when the angle measure is 0 degrees. And the only time that cosine, or the x value, is equal to 11, well, again, no solution inside of a unit circle. There's no spot inside this unit circle that has an x value equal to 11. So no solution from that factor. For the final bonus question with 4 parts, this is just a review going back to the graphs of trig functions. See if you can determine the formula for the functions below. Remember, amplitude, the a component of our trig function, is the height from the midline to the peak of the wave. So in this case, the height between midline and the peak is 2, so our a value is 2. The b value comes from this computation, 2 pi divided by t, and this is good for sine and cosine. For tangent functions, it's 1 pi divided by t, but for sine and cosine waves, it's 2 pi divided by t, where t is the horizontal distance between the two peaks or two valleys. It's the length of the period of the function. So in this case, t is equal to pi. 2 pi divided by 2 tells me that our b value in this case is 2. C and D represent our shifting, and if you see this graph as a cosine wave, if you see this as a cosine wave instead of a sine wave, then there is no shifting involved. The peak is where the graph itself starts. If you see this curve as a sine wave, then you might picture that this is the starting point, and you would say that the CD values would be some combination of pi or some fraction of pi. To make things easier and to make our answer as efficient as possible, I am going to consider this a cosine function that hasn't been shifted. And with an a value of 2, a b value of 2, and a c and d value of 0, I would report the final solution like this: a and b. And, well, I guess it's worth noting, a times our trig function evaluated at b times x plus or minus the c value plus d. Now, a lot of times we write this as x minus c, and that's just a reminder to do the opposite of what's being shown on the interior in order to obtain the desired result. For part B, our a value is 6 because the midline to the peak is 6 units. Our t value is 1. The cycle completes in 1 horizontal unit. So 2 pi divided by 1 means that our b value is equal to 2 pi over 1. So we've got an a and a b value. I'm going to treat this like a sine function, which is supposed to start at the origin here. This one does. So the c and d value are 0 each. So for part B, I like 6 times sine times 2 pi times x with no c or d movement. For part C, I see that our t value is 10. So from -1 to 9 is 10 units. It takes 10 horizontal units for the cycle to complete. So our b value is 2 pi divided by 10, or 1 pi over 5. Our height from midline to peak is 5 units, so our a value is 5. And I'm going to treat this curve like a sine function that's been shifted to the right. Now, the starting point of the sine wave is always halfway in between its cycles, beginning and end. So halfway, or half of 10 horizontal units is 5. So I know we're 5 units to the left from 9, 5 units to the right of -1, and that puts us at 4. There's no vertical shifting going on here, so my d value is 0, but our c value is 4. And so with that, with those components known, I'm going to argue that this is our equation for that graph: 5 sine times pi over 5 quantity of x minus 4. And again, I'm using -4 because I'm shifting this graph to the right 4 units, so I'm using the opposite of what you might expect. Notice, too, that I'm using the double set of parentheses. That's what I would prefer. I think Math Excel might lead you in a different direction, but this solution would be fine for me. I think they like to distribute and eliminate the double parentheses, and I'm personally not a fan of that. So for part D, this has got, well, a little bit more work involved. You've got to interpolate just a little bit more. Our t value is 12 pi units, so the horizontal distance between the starting and ending of the wave is 12 pi. 2 pi divided by 12 pi reduces to 1/6, so we've got a b value of 1/6. The a value might be a little bit hard to see right away, but the scaling on the left helps. So from 3 to the midline to 9, if that was cut evenly or evenly distributed, we'd have 3, 6, 9 units. So that tells me that this midline is 6. From 6 to 9 gives me an a value of 3. The other trick, of course, is to measure the high point and the low point and find the average between those two. well, I'm sorry, subtract those two and divide by 2, and that gives you your A value. If you do just find the average, that gives you your D value. So the middle between 3 and 9 is 6. If I treat this like a cosine function where the peak is supposed to be at the origin, then there is no horizontal shifting. If you wanted to treat this like a sine function, you might find this position over here where I just drew this little plus sign as your new origin, and you would have a C value. But if I don't want to shift this horizontally by considering this a cosine function, that's perfectly fine. And we've got 3 times cosine 1/6 x with the plus 6 on the outside. Plus 6 because the vertical movement is not going to be reported as the opposite. It's going to be reported as we would expect since it's on the outside of our grouping symbol. And there you have it. That was our practice test from last week. I know that this video was quite lengthy, but hopefully you found a component within the video that was particularly useful, and you're able to kind of interpret your approach and decide what may need to be different for the real test next week. As always, please let me know if you have any questions. You can send me an email or reach out to me through Schoology, and we'll try to set up a time to discuss. Thanks for watching.